Okay. Okay, live. Hello. Use this to see the chat. Okay. We are live. Let me quickly open the whiteboard. Okay, we have the whiteboard here. Cool. Hi everyone, and welcome to another interview series. So again, I believe it was okay. Let me have to log in as well. Let me log in quickly. Okay, so go to contest. Hmm. So yeah, we have three problems again, and we'll be trying to solve all of them. So I hope, yeah, the code is not written. All right. So let's start with the first problem. The first problem is for this number. It's a pretty simple problem. Like, understanding the problem is pretty simple, but however, like, the solution, we have to think a bit. So the problem is, we are given ARR, an array ARR of size n. For every element in the array, the task is to find the index of the furthest element from the array to the right, which is smaller than the current element. So you have to find the farthest element to the right side, which is smaller than the current element, and if so no such element exists, you have to print -1. Hey Kamlesh, you have to print -1. So you have to it uses a zero based indexing. So 3 1 5 2 4. So for 3, what is the element smaller than 3 and is on the right farthest on the right hand side? It is, what are the elements smaller than 3 on the right hand side? 1 and 2. Which one is farthest? 2. So the output for ARR3 is the farthest. Okay, the index will be 0 1 2 3. Index will be 3, right? So for the first element it's 3. Then for 1, there is no element on the right hand side which is smaller than 1. So yeah, let's see. So it will be -1. Then again for 5, the farthest element will be 4, which is less than 5, and the index for this will be 4. So 4 will be here, -1 -1, right? So this is the answer. Okay, let's understand how do we solve this. Okay, let's understand how do we solve this. So let's take this example 31524. Let's take the example 31524. Okay, so we have the example 31524, right? DQ plus stack, I use stacked direction, soft, yeah, binary search. Okay, so we will be also using suffix mean and binary search to solve this problem. So yeah, the idea is that, okay, we want the farthest element on the right hand side which is smaller than the given element, right? So let's take one array, a special array, which is called the suffix mean, right? So we know about suffix sum, prefix sum. What is prefix sum? From the front you are taking sum, right? What is suffix sum? From the back you are taking sum. So similarly, prefix mean will be from the front you are taking mean. So basically prefix mean, let's call it PM, prefix mean of I will be equals to the minimum of prefix mean of I minus 1 comma a of I, right? So this will be the formula for prefix mean. Similarly, we will use something special called as suffix mean, right? What is suffix mean? What is the minimum on the right hand side? What is the minimum element on the right hand side? So suffix mean of I will be what is the minimum element from I plus 1 to I to n minus 1, right? What is the minimum element from I to n minus 1? So we will use this array. So let's compute the suffix minimum of this. Let's call it SM, suffix minimum. So we'll compute from the back. So suffix minimum of 4 will be 4. For 2 it will be 2. For 5 it will be 2. What is the minimum element from this index, that is 0 1 2 2 to 4? What is the minimum element? It is 2, right? So 2 will be the minimum element. After that 1 will be the minimum element. 3 1 will be the minimum element. So this is the suffix mean. What is suffix mean again? It is the minimum element from a suffix min of I will be the minimum element from I to n, right? I to n minus 1. What is the minimum element from I to n minus 1? Now, why is this helpful, right? Let's understand how this will help us compute an answer. So if we want to compute the answer for index I, right? We want to compute the answer from index I. What do we want? What is the rightmost element? What is the rightmost element that has that is less than a of I? What is the rightmost element that is less than a of I, right? So for I, we will find this. What is the rightmost element which is less than I? For 5, isn't it 4? It will be 5. It will be 2, right? Suffix minimum. Suffix minimum. This is not the answer. This is the suffix minimum. The definition of suffix minimum of I is the minimum value in the range I to n minus 1. The array range I to n minus 1. In the range I to n minus 1, that is from 5 to 4, which is the minimum value. It is 2, right? So that's why it is suffix min. So this is basically what suffix min stands for. Not next smaller element, it's suffix min is suffix min. What is the minimum element from I to n? Right. So what is the answer? Answer for I, right? Answer for I. That's what we are computing. Answer for I. Now, how do we compute this? Using suffix minimum, definitely. What do we want? We want the answer for I will be what is the farthest element from I which is smaller than a of I. What is the farthest element of I which is smaller than a of I? Now think about it like this, that let's say if there is an element j, right? If there is an element j which is less than a of I, if there is an element j which is less than a of I, then for all the elements before, like for all the indices before j, the suffix minimum will contain suffix minimum of k for any index k from I plus 1 to j. From I plus 1 to j, for any index k, suffix minimum of k will definitely be less than a of I. Why? Because suffix minimum, we are carrying forward the minimum. So let's say all the elements in between are greater than a of I, right? But j, then the suffix minimum will be the element at j itself, because a of j is less than a of I. We have already said that a of j is less than a of I. So for any j where a of j is less than a of I, all the elements on the left hand side are definitely less than a of I. So the answer for us will definitely lie towards the right hand side. Why will the answer lie towards the right hand side? Because j is definitely a possible answer, right? If the answer is not j, it will be on the right hand side of j. We want the farthest element, right? On the previous part, we don't have to check because we are sure the suffix minimum of k for all the elements from I plus 1 to j will be less than a of I, because a of j is less than a of I. That makes sense, right? Like if a of j is 1, right? Here if a of j, or let's say 2 is less than 3. So here in all these elements, all these places, the suffix minimum will definitely be less than equal to 2. Like for 5 it will be 2, for 1 it will be 1, which is less than equal to 2, right? So for all the places it will definitely be less than equal to 2. So 2 is definitely a better answer. 2 is the answer, or the answer will be on the right hand side of 2. So in that case, our search space will be taking if this is the condition, our search space will be from j to n minus 1. Our search space will be on the right hand side, that is j to n minus 1, because there the answer will be there. Either it is j or somewhere on the right hand side of j. Let's consider the other example, right? Let's consider the other example. The other example is let's consider the other case. The other case is a of j is greater than a of I. If a of j is greater than a of I, or let's say not a of j, rather if suffix minimum of j is greater than a of I, if suffix minimum of j is greater than equal to a of I, that means what? All the elements in the range j plus 1 to n minus 1, suffix minimum elements in the range j to n minus 1, they are not the answer. So the answer definitely lies on the left hand side. So we will discard this entire range and we will continue our search from I plus 1 to basically j, because we will not j will never be the answer. So our high will be pointing to that some place that is never containing the answer. So this is the logic. So this basically proves that we can do binary search on the array. So for a case when the suffix minimum is less than a of I, so definitely the answer is on the right hand side. So we'll take the second half. Otherwise we'll take the first half and continue a search on that. So this is the logic for solving the problem. So let's understand with this test case 31524, right? So let's understand here 31524. And what will be the suffix minimum? 4 2 2 1 1, 4 2 2 1 1, right? 4 2 2 1 1. What we'll do, consider the first element. For 3 we want to find. So what do we want to find? The element on the right hand side that is less than 3. So our search space will be what? Index range will be 0. This is 0. This 0 1 2 3 4. So our initial search space is 0 1 to 4, right? Our initial search space is 1 to 4. Okay, now we will check 1 to 4. So this is also 0 1 2 3 4. First of all, we'll definitely check the extremes, like is suffix minimum of 1 less than a of I, that is 3. Yes, it is. So there is the answer definitely. Is suffix minimum and we'll also check the high case. If suffix minimum of 4, that is 4 less than 3, no. So the answer is somewhere in the between, right? Now we'll do binary search. So what is the mid element? 4 plus 1 by 5 by 2 is 2, right? So 2 is the mid element. 2 is the mid element. Okay, 2 is the mid element. So a of mid, what is suffix minimum of mid? This is SM, suffix minimum. What is suffix minimum of mid? That is 2. It is 2, right? 2 is less than 3, right? 2 is less than 3. So definitely the answer is on the right hand side. The answer will be on the right hand side because we want the farthest element. So the answer will be on the right hand side. So our search space will reduce to 2 to 4. So one thing to note, low is always pointing to a valid answer index. That is, suffix minimum of low should always be less than a of I. Suffix minimum of high should always be greater than equal to a of I. So high is pointing to an index which is not the answer. High will always point to an index which doesn't satisfy the condition. So greater than equal to I. So 2 to 4 is the range. 4 doesn't satisfy, 2 satisfies. So that's why we go to this range. Okay, 2 to 4. Now again here mid is what? Mid is 4 plus 2 by 2, that is 3. Mid is 3. So now mid is this index. What is suffix minimum of mid? 2. Is 2 less than 3? Yes, 2 is less than 3. So definitely our answer is on the right hand side or this index itself. So our search space reduces to 3 to 4. Right. So low equals to mid. What we do is low equals to mid, else high equals to mid. This is what we do. Right. So low always points to answer because low is satisfying the mid is satisfying the condition for it to be answer. So 3 to 4. Right. Now we end the loop when low is less than high minus 1. When low is less than high minus 1, we will end the loop, right? We will end the loop when low is less than high minus 1. So this is less than high minus 1. So we'll end the loop here. So the answer will be low, basically 3. So the answer will be 3. What is the element or suffix minimum at index 3? Or basically we'll have to push 3 as the answer, right? So 3 is the answer. You have to write the index, and if you see the answer for 3 is indeed 3, index 3, right? So we are binary searching, we are discarding one half at a time. So let's write the code for this. It is nothing, it is just binary search, right? I am just doing binary search, nothing else. I think it will make more sense when I write the code for this. So let's write the code directly. So vector int suffix minimum, right? Initially it will be n, suffix min of n minus 1 equals to a of n minus 1. For int I equals to n minus 2, I greater than equal to 0, I minus minus, suffix min of I will be equals to min of suffix min of I plus 1. If you don't know about suffix operation, prefix operations, you have to read about it. So prefix means from the front, suffix means from the back. Suffix min of I is the minimum of in the range of I to n. So that's why we find a dynamic programming kind of solution that suffix min of I is basically the minimum of whatever we have found till now, suffix min of I plus 1 comma a of I, right? Now if after that we want to find the answer, vector int answer n and answer of n minus 1 will always be minus 1. For int I equals to 0, I less than n minus 1, I plus plus. Okay, so this is the range we are searching for. Int low equals to I plus 1, high equals to n minus 1. Right, now here we'll have a condition. If suffix mean of if suffix mean of low, right, if suffix mean of low is greater than equal to answer of is greater than equal to a of I, that means what? Suffix mean of low is what? Right now low is I plus 1. Suffix mean of I, we are telling that suffix mean of I plus 1 is greater than equal to a of I. That means what is suffix mean again? The minimum from I plus 1 to n minus 1. So all the elements in that range are greater than a of I, so there is no answer for a of I, right? So answer of I is equals to minus 1. Else if suffix mean of high is less than a of I, that means what is suffix mean of high? Right now high is n minus 1, so if the suffix mean of n minus 1, that is the last element, if the last element is less than a of I, so definitely that will be the answer. So answer of I equals to high. Else, okay, now see, if we satisfy both of these conditions, right, if we satisfy both of these conditions, what will happen? Once we have satisfied both of these conditions, this tells us that low is not the answer. This tells us that even at low it is not the answer, it doesn't satisfy the condition. This tells that high is the answer. So after this, what is left? Low is a valid answer, high is not the answer. These are the only this is what. So basically what we do is we always make low point to a answer, point to a true or a valid solution, high is pointing to a invalid solution, and our work is to bring them nearer such that low is pointing to the last valid solution, high is pointing to the first invalid solution. That's what we do. So while low less than high minus 1, int mid, and this is something, this is binary search, this is something that I've discussed multiple times. You will like find a lot of videos in this channel itself. So I've discussed this multiple times, how I do binary search. Like when you have a predicate array of the form true, false, false, true, 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 like that, in that case how do you do binary search? That is what we are doing. We are making the low point to a true, high point to a false, something like that, right? So mid equals to low plus high by 2. If a of mid is less than a of I, so that means the answer is mid is a valid solution, not a of mid, rather if suffix minimum of mid is less than a of I, so mid is a valid solution, the answer should be mid or on the right hand side of mid. So low equals to mid we do. Else it is not a valid solution, so the answer should be before mid, so high equals to mid. Why high equals to mid, not mid minus 1? Because high we are always making it point to a invalid solution that is not valid. So if high is pointing to mid minus 1, mid minus 1 might be a valid solution, we do not know that, but we are sure that mid is not a valid solution because it is not satisfying this condition, so we are making high point to mid. So mid, and finally a of I answer of I is equals to low, right, and finally return answer. So this is a simple binary search, right? We are just binary searching on the prefix array. Okay, let's run this. Okay, we are getting a proper answer, so let's try to submit this, right? So yes, so this is working, right? This is working. Just to like, I'll not go into details about how we are doing the binary search. I have done this multiple times, but just to give a small understanding about why we are doing like this. So just imagine an array, right? Imagine an array that you have where the elements are like this: true, true, true. Initially everything is true. After that, false, it becomes false and it remains false after that. So we want to find the first occurrence of true or last occurrence of true or the first occurrence of false, right? So what we do, we make the low point to the first element, high point to the last element. Now high is always pointing to a false, low is always pointing to a true, right? So whenever we'll always make this condition that low will always point to a true, high will always point to a false. So where do they end? They end at this position, right? This exact position. Low will be ending here, high will be ending here, right? So this is the exact position because high will always point to a false. So the last position where it can end up is here. Low is always pointing to a true. So the last position where it can end is here. So that is the logic we use. So every time we get a mid, let's say this is the mid, we see that mid is true. So we assign low this value because this is a possible end position. There are multiple solutions. See, there is definitely, it is possible with stacks as well, and everything. Again, like coming to the complexity, maybe with stacks you can do it in order of n, but the complexity for this is order of n log n, right? The condition with binary search for plus traversal suffix mean, it is order of n log n. So you can definitely you might be able to do it with, and I think you can do it with stacks as well, right? So that's also like, if there are multiple ways you can do it. So maybe as a homework, try different ways, right? Try to do it in using stacks, or some people are suggesting that we can do it using DQ or priority queue or something like that. So you can try similar approaches, right? So this is what I had done. So I have just explained this approach, but you should definitely try solving using other approaches. So let's go to the second problem, right? Okay, the second problem is it's yet another minimization problem. Can you send the code in chat? I would prefer not to send the code in chat again. Like if I send the code, you will have the code, so you will just type it, right? So at least try to type it yourself. At least try to write the code yourself. I would prefer that, because again, like if you write it, you will remember it later on how to write a binary search like this. So if you need help, you can pause the video or see what I've written in the code, and you can take help from there. But definitely, I will want you to write the code yourself, right? So let's come to this yet another minimization problem. So our geek is opening a new training institute. He is planning out timing of all the batches in the institute. Given the start and the end times of all the batches, help him find the minimum number of rooms needed to conduct all the batches. So minimum number of needed to conduct all the batches. At any given instance of time, only one batch can be conducted in one room. Also, the same room can be used when the end time of one batch is equal to the start time of another batch. Okay, so what it tells is, we are given the starting and the ending times of the classes, right? There are multiple classes that will be going on. We are given starting and ending time of all the classes. Let's say let's consider your college, right? So you're going to your college, you have your, there are multiple periods, right? There's let's say mechanics, there's computer science, there's data structures, algorithms, a lot of these things, right? So there are multiple classes. Every class, for every class, you know the starting time and the ending time. There might be overlaps as well. It is not like they will occur one after another. There might be overlap. Like let's say there is a machine learning class, there's a web development class, there's a like, these are specialization, right? So they can occur in parallel. So you are given the starting and ending time of all the classes. You have to find what is the minimum number of rooms, so that all the classes can run smoothly. That is, when multiple classes are happening parallelly, let's say 5 classes are happening parallelly, you would need 5 rooms, right? Because all of them are happening parallelly. So you would need 5 different rooms for each of them. So for that the answer will be 5. So what is the minimum number of rooms that you will need to have all the classes? And it is also said that if the ending time of one class is equals to the starting time of another class, then you cannot use the same room. You cannot use the same room, right? You cannot use the same room. So for example, we have one class starting at 0900. This is how the times are given: 0900, 0940, 0950. So 0900, it ends at 9:10. Let's write it down. Okay, it starts at 9 a.m. it ends at 9:10. This is one class, right? What about the second class? The second class starts at 9:40, ends at 12. The second class starts at 9:40. 9:40 a.m. and ends at 12 p.m. Right. Okay. The third class starts at 9:50 and ends at 11:20. 9:50 and 11:20. So it starts at 9:50, ends at 11:20. So this is 11:20 a.m. 9:50 a.m. it starts at, right? Okay. The fourth class starts at 11 a.m. and 11:30, ends at 11:30. 11 to 11:30. So 11 here to 11:30, somewhere here, right? Fourth class. So 11 to 11:30. The fifth class is 15 to 19, that is 3 to 7, 3 p.m. to 7 p.m. So it's here 15 to 17 or 19, was it? 15 to 19, 18 to 20, 15 to 19. And the last class is 18 to 20. 18 to 20. So how many classes are needed, right? We have to find how many classes are needed. Yes, this is very similar to activity selection problem as well. Like how many activities that you can do, or in fact there is a similar problem, right? In Geeks for Geeks only, this problem is very similar to the train junction that I've already discussed before. There is there are trains coming in the railway station, the railway station problem, right? How many platforms do you need? Minimum number of platforms. So there are trains coming in at different times. How many platforms do you need? So that's basically how the exact problem. So here if you see, there is only one class going on in this entire duration. In this duration you will have two classes, but if you see this duration, that is after 11, there are three classes going on, right? Three parallel classes are going on. And here also two classes are going on, right? So here also two classes are going on. So what is the maximum number of classes that are going on in parallel? 3, right? At any point of time, 3 classes is the maximum number of classes that are going on in parallel. So the answer for this problem will be 3. We would need 3 classrooms to have all the classes, right? So the answer for this will be 3, right? 3. Yes. So this is the question. So how we can do this? A very simple, whenever you have ranges, right? So what you essentially have to find, if you think about it, what is the essential question? The question is, you are given ranges, right? L to R, you are given ranges. What is the maximum number of ranges that can intersect at any point in any point? So what you have to find is maximum number of ranges intersecting at a point. That is what you have to find. Maximum number of ranges intersecting at a point, that is what you have to find. So there are multiple ways to solve this, but the way that I prefer is using a hash map, right? So what you do is you have a range L to R, right? Plus A of R plus 1 minus, right? And then you take a prefix sum. This will give you, for any point, this will give you what is the total number of ranges that are intersecting at that point. How does this give that? Let's understand. See, R is definitely greater than L, right? Because it is a valid range. You are going, right? Let's say this is L, this is R. You are R plus 1 and this is R. You are going here. Let's say you are doing prefix sum, right? So you are having some answer, like count till now. When you come to L, you do count plus 1. So after this, your count becomes count plus 1. Basically, the presence of this L to R range is added to the count. Now you are going. Whenever you come to R and then you come to R plus 1, you do A of R plus 1 minus. So that is count minus 1, right? Count minus 1, that is whatever is the current count, the count plus 1 minus 1. So the presence of the current range is gone, right? So this is how in the range L to R you will get the presence of the current range, right? Let's understand this with an example. So let's say we have some ranges. Now we have reduced this problem into range number of ranges intersecting. So let's say we have some ranges like this: 1 to 5, 2 to 4, 3 to 6, uh, 5 to 7, right? Something like this. 5 to 7 and 8 to 9. Okay. So see, what do we do in the array? We will take a of 1 plus plus. So initially everything is 0, right? Everything is 0. So let's write the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll do a of 1 plus plus, right? A of 1 plus plus. So a of 1 plus plus means 1. A of r plus 1, that is 5 plus 1, 6. A of 6 is minus minus. So 0 minus 1 is minus 1. A of 2 plus plus. A of 2 plus plus. 2 is 1. A of 4 plus 1, 5. 5 is minus minus. So 5 is minus minus. A of L, that is 3. 3 plus plus. 3 is plus plus. A of 6 plus 1, that is 7. 7 minus minus. So 7 minus minus. A of 8 plus plus, or let's call it 7 to 9, right? Let's call it 7 to 9. A of 7 plus plus, so 7 is minus 1. Minus 1 plus 1 is 0. A of 10 minus minus, so 10 minus 1. Okay, this is the array that we have. Now if we take a prefix sum, see what will happen. 0, 1, this will become 1 plus 2, that is 2, right? This will become 2. This will become 3. This will remain 3. This will become 2. This will become minus 1, 1. This will become 1. We are taking prefix sum, right? We are just taking prefix sum. So this will remain 1. This will remain 1. This will become 0. Now see, consider any index, right? Consider any index. For any index, this array gives you number of intervals that are crossing that index, right? Let's consider 3. Index 3, we are telling that 3 intervals are crossing this index. Is it true? 3 intervals. This is crossing 3. This is crossing 3. This is crossing 3. So there are 3 intervals that are crossing in index 3, right? So that's how we get, right? Similarly, 7, 6 or 7. 7, one index is crossing, right? So one index is crossing 7. See, 5 to 7. 5 to 7, 7 plus 1 we should have done. I think we had 5 to 7, 7 to 9. We have not taken 5 to 7 probably. But anyways, like you get the idea, right? Let's take the example of like 4 or something, right? So in or 5 and 5, 2 indices are covering, right? 1 to 5 is covering, 2 to 4, 3 to 6 is covering. We have not taken 5 to 7 at all. We have not considered this. So 5 to 7 is not there. Anyways, this is the logic, right? So if you see what exactly happens when you come here, you did a of 1 plus plus, right? So when you come at 1, your count increased by 1. When you are leaving 5, when you came to 6, your count decreased by 1. So 1 to 5, this range, the presence of this range is gone from the count. So that is how, so the maximum parallel is 3, right? You get 3, so the answer will be 3. You would need 3 classrooms, or the maximum number of ranges that are intersecting is 3. So that will be the logic. So let's try to write the code for this. Okay. Start and end. Let's consider vector int. Let's call it frequency. Or frequency. The what is the maximum it can go to? 2359 actually, or 60. So let's take 61. Right. Frequency 2361 0. Okay, so for int I equals to 0, I less than start dot size I plus plus, frequency of start of I plus plus. This is a very popular technique, right? This is, in fact it is called range update point query. So if you have range updates and you have point queries, you can do something like this if you are processing offline. Right, like after everything you have to tell how many ranges are passing from an index or how many updates has occurred in an index. You can do it like this. So frequency of start minus minus, frequency of end I plus 1, sorry, I end of I plus 1 minus minus, right? So we have considered them. Now we have to take prefix sum for int I equals to 0, I less than 2361, I plus plus, frequency of I equals to frequency of I minus 1 plus equals to frequency of I minus 1, and we'll start the loop from 1, not 0, right? We'll start the loop from 1. So we have the number of so int max element is equals to frequency of 0 for int I equals to 1, I less than 2361, I plus plus, max element equals to max of max element and frequency of I, and return frequency, return max element, the maximum number of lines that can pass. So max element return. Why we are taking n plus 1 and not simply n? Because it is said that we cannot use the room if the end time of one batch is equals to the start time of another. So if you do end minus 1, in end if you do minus 1, then when you reach end, the count of that reduces, right? So if you had one interval that ends at end and another starts at end, let's say 3, one interval ends at 3, one interval starts at 3. So if you do 3 minus minus, the count reduces to 0, right? Now again 3 plus plus, the count increases to 1. So we'll know that there is only one class that's going on at time 3. But at time 3 it is said that you cannot have two classes if it is ending at that time and starting at that time. You cannot have them at the same time. So that's why n plus 1. Okay, so 3 is given. So let's submit this. Okay, so this is also done. Okay, pretty simple problem. This is basically same as in Geeks4Geeks only we'll find the minimum platforms question, and exactly same, like in fact the input style is also the same thing, it's also the same, right? So exactly the same, and I've also discussed that problem before in one of the classes. So it's the same thing, right? Again, okay, so this is very simple, like I'm not wasting a lot of time on this. So we can go to the third question, that is process dependencies, right? I'll go with C++. Okay, so it tells that okay, it tells that we are given an operating system. We are given an operating system that contains n processes. The OS needs to complete all the processes, but some processes are dependent on other processes. That is, some operations can be completed only after the completion of other processes. Given array of dependencies I is equals to ai comma bi, that indicate ai must be completed. In order to complete process bi, find the order in which processes should be scheduled, right? So it is told that we are given dependencies, we are given a graph of dependencies. There are some processes, and some processes depend on another process to be completed so that it can be completed. So we are given that find the order in which the processes should be scheduled so that to complete all the processes, right? And it is given, we are given dependencies where ai must be completed in order to complete process bi, right? Ai must be completed if you want to complete bi. So ai must come before bi, right? So ai must come before bi. T210, yes. Okay, so we have the dependency graph like this. We have the dependency graph like this, that is 1 to 0, 3 to 0, 2 to 0. So what is the order in which? So basically it tells that to complete 0, we have to have 1 completed, 2 completed and 3 completed. So they should be completed first. So one way of scheduling is 3210. Another way can be 1230, or another way can be 2310, but 2031, that is not a valid way. 0 should be completed only after all others are completed. So all others should be scheduled before scheduling 0. So that's why one answer will be 3210, right? So similarly here we have something like this. 4 is connected to 0. So 4 is right, 4 0 is dependent on 4, kind of 0 is dependent on 4. Is the okay, we have the graph reversed, so we should have done no, actually this is correct. Okay, this is correct. So this is correct, left to right. Okay, this is correct. So 4 should be completed before 0. 4 should be also 1 depends on 4. So 4 should be completed before 1. Similarly, 1 should be completed before 3. 2 should be completed before 3. 5 should be completed before 2. So one way can be 542130, 542130, right? 5 is completed, so it is not dependent on anything. 4 is completed, then 2 is completed, 5 is already completed, so 2 can complete now, so 2 is completed, then 3 is completed. Sorry, after 2 there should be 1 is completed because 4 is completed, so 1 can be completed. 3 is now completed, 0 can be now completed because 5 and 4 both are completed. So that can be one way to do this, right? Now this is very simple question. Like if you think about it a bit carefully, what it exactly tells you is to find a topological sorting. It is exactly telling you to find a topological sorting of a graph. What is a topological sorting? Topological sorting of a directed graph is ordering the graph or ordering the nodes in such way that all the edges are moving from left to right. So if you see, left to right means 1 to 0. Left to right, if the edges are always moving from left to right, that is a process that needs to be completed before the completion of another process is actually completed before. So all the edges are moving left to right, right? So kind of this makes sense. So if you see here, if you arrange it in a topological sorted way, let's say 3 to 1 0, all the edges, that is 3 to 0, 2 to 0, 1 to 0, all the edges are moving from left to right. So this is basically, this question is nothing but finding a topological sorting of a graph. So we will directly go into writing the code for this. Like there is no explanation that we can do, right? This is simply finding a topological sorting. That is, all the edges will be arranging the nodes in such a way that the edges will only move from left to right. Because the right should be completed later, the left should be completed first, and after that the right should be completed. So this is basically finding a topological sorting. So let's go ahead with the topological sorting. So order processes. So we have the dependence, we have the graph written here. These are the edges, right? This is the edges. So we have to find the topological sorting. So let's take a graph. Vector int g, vector int g star g, g equals to new vector int of size n. I think it should be n plus 1 or n, zero based indexing, right? N. And then for int I equals to 0, I less than dependencies I plus plus. So 0 to 1 means 0 to 1 means what? 3 to 0 means 3 will be pushing 0, right? So 1 second. So 3 will be pushing 0. So g of dependencies I of 0 dot pushback dependencies I1, right? So we are pushing the dependencies. Now what we'll do, we'll do a topological sorting. So how do we do that? We'll maintain a stack int x, and also a visited array. So vector bool visited, and visited also will be vector bool n, and everything will be false. So DFS for int I equals to 0, I less than n, I plus plus, if not visited I will do DFSI, if not visited I, DFSI. So DFSI void DFS int s, g of s, visited of s is equals to true for int v belongs to g of s, if not visited v, DFS v, and x dot push, after at last will push s, right? X dot push s. So we have it in our topological sorted way. Now we'll have to move this to a vector. So vector int answer while not x dot empty answer dot pushback x dot top x dot pop return answer. Okay, return answer. So let's try to run this. I less than dependencies dot size, sorry, merge sort. Okay, so this is giving 1. So let's try to submit this. First question tried with merge sort got TLE. Can you tell me what's wrong? How can I tell without seeing your code? But it's not merge. It will not be by merge sort. It should be basically, maybe you are doing merge sort for every time you are doing merge sort or something like that. Or I'm not sure how you're solving. So it depends on your implementation. Make sure to check the complexity. The time complexity that will be allowed will be n log n. So you can try seeing if your complexity is indeed n log n or it's n square log n or something. Right. So make sure you see that. Anyways, this is also solved. So pretty simple question, like you just had to do the topological sorting and that was it. Right. So we have done topological sorting like this. So you take a stack, you do the DFS and then you push into the stack. So after that, and you do this for like as long as you have some unvisited vertices, and finally you return the order. Right. So that's about all the questions today. I think we have solved all the questions. Yes, so we have solved all the questions. So yeah, thank you guys for joining in, and if you have any doubts, make sure like just see the explanation again. I try to explain as best as possible, and these are pretty simple questions. Like there are multiple questions, similar questions already there in the platform. So you can like for example, this was just topological sorting, so there was nothing to explain, right? This problem is same as minimum platforms. So I've already explained that, and I've solved similar questions multiple times. It's just range overlap. So there are multiple ways to do that. There is greedy, there's hashing the way I did, and multiple other ways, right? So, and farthest number, this was a bit different, but again, like that's I already tried to explain that. It's you can use multiple approaches again here. So I'll recommend you to try using different approaches. So yeah, that's about today. Thank you guys for joining in, and I'll be seeing you next Sunday. Thanks. Bye.